Okay, so let's look at another example of diagonalization. This time we're not going to go through the process of diagonalizing a matrix. We're just going to confirm whether or not the matrix is diagonalizable to begin with. So the matrix that I'm looking at here is a 4 by 4. If I were to go through the entire process of diagonalizing this thing, which would involve finding all of its eigenvalues and all that, and normally in a 4 by 4 case that would be kind of a lengthy process, but this is a nice matrix in the sense that it's upper triangular. You'll notice we have zeros below the main diagonal. We know from upper triangular or any triangular matrix, the eigenvalues of that matrix are the main diagonal entries. Now in this case, you'll notice the 4 eigenvalues that we get are 1, -1, 5, and 3. So these eigen values are each going to have their own eigenspace associated with them. Each eigenspace has to have a basis of at least one vector, because that's true of any vector space aside from the trivial vector space. So that means we're going to have at least 4 vectors. Now we're actually going to talk about this a little bit later. We actually can't have any more than 4 vectors in total. That'll come up in a discussion of algebraic and geometric multiplicity at the end of this video. But what that means is that I'm going to have a total of 4 basis vectors, one for each eigenspace, which I can throw into my matrix P. That set consisting of those 4 vectors will be linearly independent because of the theorems that we talked about before. And so that means I'm going to have a set of n linearly independent eigenvectors, which means this is going to be diagonalizable according to that previous theorem that we talked about. So this one I'm not really writing anything because I'm not working anything out. I left myself some space and now I realize I didn't need to do that. It's more of just a verbal argument for why this is diagonalizable. But again, because I have 4 distinct eigenvalues, I'm going to have a set of 4 linearly independent eigenvectors coming from the bases of those eigenspaces, and that would make this diagonalizable. Okay, let's go ahead and move on to the last couple of things for 5.2. We're going to shift the focus to an application of diagonalizing a matrix, which is raising matrices to powers. Now, we've taken powers of square matrices before. Remember, if you're going to raise a matrix to any power, it has to be a square matrix to begin with, otherwise the multiplication won't be defined. But this is something that actually arises in applications a lot. There's actually a number of cases or a number of applications where we're raising a matrix to a large power. And oftentimes the matrix itself is a very, very large matrix. We work primarily with 2 by 2, 3 by 3. Occasionally we see 4 by 4 matrices like this. In a lot of applications, the matrices that are actually being used may have on the order of millions of rows and columns. It's not practical, obviously, to do the multiplication by hand. We have algorithms to do that. But even then, the algorithms that carry out the matrix multiplication or carry out the large powers of those square matrices can be very costly in the numerical analysis sense. What that means is that it can require a lot of time to carry out all the operations in the said algorithm. So one of the things that we do a lot of in linear algebra, kind of beyond this class where we focus more on applications, is finding ways to reduce the number of operations required to carry out an algorithm. And eigenvalues and diagonalizing matrices provides a technique for carrying out large powers of square matrices without having to do a whole lot of manual multiplication. So it's all kind of vague because I haven't talked about the technique yet. Let's go ahead and move on, and we'll see where that gets applied later. So I want to begin with this theorem. If k is a positive integer, and if lambda is an eigenvalue of matrix A, and if x is a corresponding eigenvector for that eigenvalue, then lambda to the power of k will be an eigenvalue of a to the power of k. Remember, this is going to be another matrix, so it has its own eigenvalues and eigenvectors, but this establishes a relationship between the eigenvalues of a to the k and the eigenvalues of a. X will also be a corresponding eigenvector for that eigenvalue. So we're going to prove this using induction. We've kind of avoided using proofs by induction up until this point, and I could make a convincing argument for this one without using induction, but it wouldn't really be a terribly formal proof. So I want to do this one by induction. Okay, and the reason induction applies here is because we're talking about a property that applies for different positive integer values of k. I want to show that this is true for all positive integers k. That's the kind of theorem that induction is meant to prove. So I'm going to make the assumptions that are made in the theorem. We have a matrix A, it's square. Lambda is going to be one of its eigenvalues, and x is going to be one of the corresponding eigenvectors for that eigenvalue. In a proof by induction, what we do is we start with a base case. We start with the smallest positive integer, which is 1, and then show that the theorem holds when k is equal to 1. Now, there's nothing really to prove here, because when k is equal to 1, then a to the k is just a. That's a to the first power. Lambda to the first power would be lambda. And so this is true because we're assuming that ax is equal to lambda x here, with this assumption that lambda is an eigenvalue of a. So again, nothing really to prove in this case. It's just sort of true by assumption. The inductive step is what makes the theorem true for all of the other values of k. So again, if you haven't seen proofs by induction in a while, the way they work is once we've established the base case, we say, let's suppose that this theorem is true for some positive integer k. We already know at least one exists, so it's valid to make an assumption like this. Then we want to show that under this assumption, the theorem will also be true for k plus 1, so the next positive integer down the line. That inductive step will imply that the theorem will hold regardless of this integer k. So I'm using this assumption. Let's suppose that a to the power of k x is equal to lambda to the power of k x for some positive integer k. Again, that's saying that lambda to the power of k is an eigenvalue of a to the power of k with x as a corresponding eigenvector. Okay, so what I want to do is establish this thing right here. I want to show that a to the k plus 1 power times x is equal to lambda to the k plus 1 power times x, showing that lambda to the k plus 1 is an eigenvalue of a to the k plus 1 with x as a corresponding eigenvector. So what I'm going to do is just use the definition of multiplication or exponents here, a property of exponents. A to the k plus 1 is the same thing as a times a to the k. And if I group up these two terms here, this is where I get to use my assumption. The a to the k x here, we assumed, is equal to lambda to the k x, which shows up here. Now I can use the fact that lambda to the k is a scalar, and use that property of homogeneity to bring the scalar out and the a in, so basically just reverse the order of these two. So now I have lambda to the k times ax, but again, even before the inductive step, we made the assumption that lambda is an eigenvalue of a with the x as its corresponding eigenvector. So a to the x should be equal to lambda x. Multiplying these two scalars together gives me the end result. So this proves this theorem for us. In a related vein, let's talk about what I sort of opened this video with, which was, I talked about a little bit earlier, which is powers of square matrices. So I want to justify this process and then do an example where we raise a matrix to a power. So I'm going to say let's let A be an n by n matrix. Remember, this has to be square if we're going to raise it to any power at all. And I'm going to say let's suppose its eigenvalues are lambda 1 through lambda n. Okay. And furthermore, we're going to make the assumption that A is diagonalizable. This trick does not work unless A is diagonalizable. So in particular, I'm going to say if it's diagonalizable, let's suppose that A is equal to P inverse dP, where D is the diagonal matrix. And remember, the diagonal matrix will have the eigenvalues, those n eigenvalues of A, as its diagonal entries. Okay, so if I want to raise a to a power, I can change a into p inverse dp, which I did here. Now I'm going to, going from this step to this step, it seems like I made a weird jump in logic, and I'm going to justify that down here in the case where k is equal to 2. We could prove that this becomes this with another proof by induction like what we did above, but right now I just want to use this property. So if I have p inverse dp to some positive integer power, it's the same thing as just doing p inverse times the matrix in the middle, d to that power times p. Notice the p inverse and the p are not being raised to the power of k. It's just the matrix in the middle. And again, I'm going to kind of show you why that works in a second. Now the benefit of this is, yes, you're still taking a matrix and raising it to the power of k here. So you may think, well, that's not making anything simpler. I already had to raise a matrix to the power of k. But the fact that D is diagonalizable is what makes this so much easier, because for diagonal matrices, we showed back in chapter 1 that if you raise the diagonal matrix D to some positive integer power, it's the same thing as just raising its diagonal entries to the power of k, which is a considerably less difficult or time-consuming process than actually multiplying a matrix to itself k times. Okay, so to show you why this is true, I'm going to sort of justify this down here. Let's suppose I have p inverse times some matrix D times p, and D doesn't even have to be diagonal for this argument to work, but I'm just going to call it D. So let's suppose I'm raising it to the second power. Okay, what that literally means is this: p inverse dp times p inverse dp. Now if I use my associative property to rearrange the parentheses here, I can write that as p inverse dp, p inverse dp. But that's equal to p inverse di dp, right? Now the I is the identity matrix, so I can even get rid of it and just call this d times d, which is d squared, p inverse d squared p. And you notice this is the case where k is equal to 2. If I raise this to the second power, it's equivalent to just taking that exponent to the matrix in the middle and calling this d squared, right? A similar argument can be made for any positive integer power of k. You get this collapsing effect of these p inverses that are going to appear in the middle here. So let's do an example where we actually want to compute a power of a matrix. I want to find a to the 6th power, where a is this matrix right here. Now we've actually come across this matrix already. This was a matrix in the previous video that we diagonalized, and we showed that A was equal to 2, negative 1, 1, 1, 0, negative 1, 0, 1, 2 times the diagonal matrix 1, 0, 0, 0, 1, 0, 0, 0, 6 times the inverse of the first matrix, which was 1/5, 3/5, negative 1/5, negative 2/5, 4/5, 3/5, 1/5, negative 2/5, and 1/5 there. Okay. If I want to raise a to the power of 6, then that's the same thing as simply raising the taking this kind of factorization of A, this product of 3 matrices, and only raising the matrix in the middle to the power of 6. And because it's diagonal, that's the same as raising only its diagonal entries to the power of 6. So that gets me this. Same matrices on the outside. I don't have to raise these to any power. But I'll have 1 to the 6, 0, 0, 0, 1 to the 6, 0, 0, 0, 6 to the 6th. And then this guy right here. okay? From here, this is easy enough to raise these to a power. The 6 to the 6th power gives me a fairly large number, but then I would just multiply what's left so that I get a single matrix as a result. This one ends up coming out to 9,332, negative 18,662, 9,331. You're going to notice a lot of these numbers look very similar to each other, and that's fairly typical. There's a reason why that happens. Negative 9,331, 18,662, negative 37,324, and 18,663. So again, if I were to try and multiply this 3 by 3 matrix to itself 6 times, that would take a long time if I were doing that by hand. This cuts down on the amount of time that takes. Imagine doing this if I were raising a to the 100th power. That would take an extremely long time to do by hand, but this technique would take essentially the same amount of time if I raised it to the power of 100, because the only thing that's really changing is that each of these diagonal entries are being raised to the power of 100. I'd get a really big number here, but the rest of the work is about as time consuming as this was. All right. Very last thing, we're just going to take a minute to talk about this. Algebraic and geometric multiplicity. This is something that's usually talked about in a second course in linear algebra. So in a sense, it's kind of an optional topic here, but it sort of gives a clearer picture of knowing when a diagonal matrix is, when a matrix A is diagonalizable and when it's not. So there's a couple of terms that we define here. Two different concepts of what multiplicity mean. If you have some eigenvalue for a square matrix A, I'm going to call it lambda naught. That eigenvalue has an eigenspace that's associated with it. An eigenspace is a vector space. So as a vector space, it has a dimension. We call that dimension the geometric multiplicity of the eigenvalue lambda. Geometric multiplicity is the dimension of the eigenspace corresponding to that. We call it geometric because, remember, the eigenspaces are subspaces of Rn for some value of n. N would be would come from the dimensions of A. So by picturing it as a subspace of Rn, in particular, say it's R3, those subspaces would look like lines or planes or all of R3 or something like that. So there's sort of a geometric quality to those vector spaces. In addition to that, when you compute the eigenvalues of a matrix, we do it by finding a characteristic polynomial, which we typically factor down into linear factors. The number of times the linear factor lambda minus lambda naught, there's the eigenvalue again, appears in that characteristic polynomial is what we call the algebraic multiplicity. It's the same multiplicity that we typically talk about in a pre-calculus class. You're going to usually see the algebraic multiplicity as the exponent on that factor when you get your characteristic polynomial. Okay, so two different concepts of geometric and algebraic, two different concepts of multiplicity, and together they give us a condition under which we can determine whether or not a matrix A is diagonalizable. So here, if we assume A is a square matrix, there's two parts to this. If for every eigenvalue of A, the geometric multiplicity is always less than or equal to the algebraic multiplicity. And without getting too deep into this, this is what basically prevents an n by n matrix from having more than n linearly independent eigenvectors. It's not the only reason for that, but you can construct an argument from this. Part B is the one that really wraps up the question of diagonalizability. A matrix A is diagonalizable if and only if its characteristic polynomial can be expressed as a product of linear factors and the geometric multiplicity of each eigenvalue is equal to the algebraic multiplicity. So in other words, A is diagonalizable if and only if for every eigenvalue that you have for that matrix, both the algebraic multiplicity and the geometric multiplicity are equal to each other for each one. In one of our previous examples where we determined that a matrix was diagonalizable. Let's see if I can find the one I'm thinking of. So this right here, okay, we can see this confirmed. Here's our here's our characteristic polynomial. I have the eigenvalue 1, and notice it's raised to the second power. That means that the eigenvalue 1 has an algebraic multiplicity of 2. When I found a basis for its eigenspace, that basis had 2 vectors, which means it has a dimension of 2, or in other words, the geometric multiplicity of the eigenvalue 1 is also 2. The geometric multiplicity and the algebraic multiplicity were equal to each other. Again, I did that here. For the eigenvalue 6, it shows up only one time as a factor in this characteristic polynomial. Its eigenspace had only one vector, so the geometric multiplicity and the algebraic multiplicity of 6, the eigenvalue 6, are both equal to 1. That's what made this diagonalizable, that matching of algebraic and geometric multiplicity. We're not going to use that concept for a whole lot. I just wanted to throw that in there because this is it's a critical theorem in the question of diagonalizability, and it's a good way to end this video. And that's going to be it for 5.2.